Welcome to your comprehensive guide on algorithm mastery for interview success. Today, you'll learn the essential concepts that form the backbone of technical interviews. From understanding time complexity analysis to implementing dynamic programming solutions, this journey covers everything you need to excel. The core concepts include time complexity analysis, space optimization, and systematic problem-solving approaches. Advanced topics span dynamic programming techniques, greedy algorithm strategies, and recursive pattern recognition. These skills are fundamental for any software engineering role and will give you the confidence to tackle even the most challenging interview questions. Time complexity is the foundation of algorithm analysis. It measures how the runtime of an algorithm grows as the input size increases. Big O notation provides a standardized way to express this growth. O of 1 represents constant time, meaning the algorithm takes the same time regardless of input size. O of log n is logarithmic time, common in binary search algorithms. O of n represents linear time, where runtime grows proportionally with input. O of n log n is linearithmic, typical of efficient sorting algorithms like merge sort. O of n squared is quadratic time, often seen in nested loops. O of 2 to the power n represents exponential time, which should be avoided for large inputs. Understanding these complexities helps you choose the most efficient solution for any problem. Bubble sort is one of the simplest sorting algorithms to understand. The algorithm works by repeatedly stepping through the list, comparing adjacent elements and swapping them if they're in the wrong order. The process is repeated until the list is sorted. In the implementation, the outer loop runs n times, while the inner loop compares adjacent elements. When r of j is greater than r of j plus 1, they are swapped. The algorithm has O of n squared time complexity, making it inefficient for large datasets. However, it has O of 1 space complexity since it sorts in place. Bubble sort is stable, meaning equal elements maintain their relative order. While rarely used in practice due to poor performance, it's excellent for learning sorting fundamentals and understanding algorithm analysis. Quicksort is a highly efficient divide and conquer sorting algorithm. It works by selecting a pivot element and partitioning the array around it. Elements smaller than the pivot go to the left, larger elements go to the right. The algorithm then recursively sorts the left and right subarrays. The implementation begins with a base case. If the array length is 1 or less, return it unchanged. A pivot is chosen, typically the middle element. The array is then divided into 3 parts: elements less than pivot, equal to pivot, and greater than pivot. Quicksort recursively processes the left and right partitions. The best and average case time complexity is O of n log n, making it very efficient. However, the worst case is O of n squared when the pivot is always the smallest or largest element. The space complexity is O of log n due to the recursive call stack. Quicksort is cache-friendly and performs exceptionally well on large datasets. Binary search is an efficient algorithm for finding a target value in a sorted array. It works by repeatedly dividing the search space in half. The algorithm compares the target with the middle element and eliminates half of the remaining elements in each step. The implementation uses 2 pointers, left starting at 0 and right at array length -1. In each iteration, calculate the middle index as left plus right divided by 2. If the middle element equals the target, return the index. If the middle element is less than the target, search the right half by setting left to mid +1. Otherwise, search the left half by setting right to mid -1. Continue until the target is found or left exceeds right. Binary search has O of log n time complexity, making it extremely fast even for large datasets. The key requirement is that the input array must be sorted. This algorithm demonstrates the power of divide and conquer strategies in achieving logarithmic time complexity. Recursion is a programming technique where a function calls itself to solve smaller instances of the same problem. Every recursive function must have 3 essential components. First, a base case that stops the recursion and prevents infinite loops. Second, a recursive case where the function calls itself with modified parameters. Third, progress toward the base case with each recursive call. The factorial function perfectly demonstrates these principles. The base case returns 1 when n equals 0 or 1. The recursive case returns n multiplied by factorial of n minus 1. Each call reduces n by 1, ensuring progress toward the base case. The call stack visualization shows factorial of 3 expanding to 3 times factorial of 2, then 3 times 2 times factorial of 1, finally evaluating to 3 times 2 times 1 equals 6. Recursion is particularly powerful for tree traversals, divide and conquer algorithms, and problems with self-similar substructures. Understanding recursion is crucial for mastering more advanced algorithms like dynamic programming. Dynamic programming is an optimization technique that solves complex problems by breaking them into simpler subproblems. It's particularly effective when problems exhibit two key properties. First, overlapping subproblems occur when the same subproblems are solved multiple times in a naive recursive approach. Second, optimal substructure means the optimal solution to the problem contains optimal solutions to its subproblems. Dynamic programming can be implemented using two main approaches. Top-down memoization uses recursion with result caching to avoid redundant calculations. Bottom-up tabulation builds solutions iteratively from the smallest subproblems upward. The technique transforms exponential time algorithms into polynomial time solutions by storing and reusing previously computed results. Dynamic programming is essential for solving optimization problems like shortest paths, longest common subsequences, and resource allocation. Mastering this technique dramatically improves your problem-solving toolkit and is frequently tested in technical interviews. The Fibonacci sequence perfectly illustrates the power of dynamic programming optimization. The naive recursive approach has exponential time complexity of O of 2 to the power n because it recalculates the same values repeatedly. The dynamic programming solution transforms this into linear time O of n. The bottom-up implementation creates an array dp to store computed values. Initialize dp of 0 as 0 and dp of 1 as 1. For each position from 2 to n, calculate dp of I as dp of I minus 1 plus dp of I minus 2. This approach computes each Fibonacci number exactly once. The time complexity improves from exponential to linear, representing a massive performance gain. For example, calculating the 40th Fibonacci number requires over 1 billion operations with naive recursion, but only 40 operations with dynamic programming. The space complexity is O of n for storing the dp array. This dramatic improvement from exponential to linear time demonstrates why dynamic programming is such a powerful optimization technique. Greedy algorithms follow a simple philosophy: make the locally optimal choice at each step, hoping to find a global optimum. The strategy involves 3 key steps. First, make the best choice available at the current moment. Second, never reconsider previous choices. Third, move to the next subproblem and repeat. Classic examples demonstrate when greedy algorithms work effectively. The coin change problem works for standard currency systems by always selecting the largest denomination first. Activity selection maximizes the number of activities by choosing those with the earliest finish times. Huffman coding creates optimal compression trees by repeatedly merging nodes with the smallest frequencies. However, greedy algorithms don't always produce optimal solutions. They work only when problems satisfy the greedy choice property, meaning local optimal choices lead to global optimality. It's crucial to verify this property before applying greedy strategies. When applicable, greedy algorithms are often simpler to implement and more efficient than dynamic programming alternatives. The activity selection problem demonstrates greedy algorithms in action. Given activities with start and finish times, select the maximum number of non-overlapping activities. The greedy strategy is to always choose the activity that finishes earliest among remaining options. The implementation first sorts activities by their finish times. Select the first activity and set its finish time as the last finish time. For each subsequent activity, if its start time is greater than or equal to the last finish time, select it and update the last finish time. The example shows activities with start and finish times in parentheses. Activity 1 from 1 to 3 is selected first. Activity 2 from 2 to 5 overlaps and is skipped. Activity 3 from 4 to 6 is selected as it starts after Activity 1 ends. Activity 4 from 5 to 7 overlaps with Activity 3. Activity 5 from 8 to 9 is selected as it doesn't overlap. The algorithm achieves O of n log n time complexity due to the initial sorting step. The greedy choice of selecting earliest finishing activities provably leads to the optimal solution, making this a perfect example of effective greedy algorithm application. Successful algorithm problem solving follows a systematic 5-step approach. Step 1. Understand the problem thoroughly by reading it carefully and identifying all constraints, edge cases, and requirements. Step 2. Work through examples manually to gain intuition about the problem structure and potential solution patterns. Step 3. Identify the appropriate algorithm patterns such as 2 pointers, sliding window, divide and conquer, or dynamic programming. Step 4. Implement the solution with clean, readable code structure and proper variable naming. Step 5. Test the solution with various cases including edge cases and analyze time and space complexity. Key techniques include mastering fundamental data structures like arrays, hash maps, trees, stacks, queues, and heaps. Important algorithm patterns include 2 pointers for array problems, sliding window for substring problems, divide and conquer for recursive solutions, and backtracking for combinatorial problems. Optimization techniques encompass dynamic programming for overlapping subproblems, greedy approaches for local optimization, and memoization for recursive solutions. Practice pattern recognition daily to quickly identify which technique applies to each problem type. Congratulations on completing your algorithm mastery journey. You've covered the essential foundations of technical interview success. Time complexity analysis from O of 1 constant time to O of 2 to the power n exponential time provides the framework for analyzing algorithm efficiency. Sorting algorithms from bubble sort to quick sort with O of n log n complexity demonstrate different approaches to organizing data. Binary search with O of log n complexity shows the power of divide and conquer on sorted data. Recursion with its base cases and recursive calls forms the foundation for many advanced algorithms. Dynamic programming with O of n complexity transforms exponential problems into linear solutions through memoization and tabulation. Greedy algorithms with O of n log n complexity provide efficient solutions when local choices lead to global optimality. Key takeaways for interview success include always analyzing time and space complexity of your solutions. Choose the right algorithm for each specific problem based on constraints and requirements. Practice pattern recognition daily to quickly identify solution approaches. Start with simple brute force solutions, then optimize using appropriate techniques. You're now ready to ace your algorithm interviews with confidence and systematic problem-solving skills.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.